So today I want you guys to look at graphing exponential functions. And our learning goal here is that students are going to understand compound interest and exponential growth and decay. But within that learning goal is this component of understanding how the graph of exponential functions work. Because if you understand how the graph works, then understanding the ideas of compound interest and exponential growth make a little bit more sense. So let's talk a little bit about the form of these functions. Anytime we're talking about an exponential function, our exponential function is going to have the form of a times b to the x. So here I'm very clearly identifying that we have a product going on here, or multiplication, but usually you'll just see it as a b to the x power, but you've got to remember that this is multiplication. So an example might be 3 times 2 to the x, and that would obviously be y equals, or maybe if we use the f of x notation, we could say f of x equals, I don't know, 10 times 1/2 to the x power. So just depending on how it's written, you want to look for the multiplication symbol or parentheses to indicate that product, but really we're looking for that variable to be in the exponent, right? What makes an exponential function is when the variable is actually in the exponent. Oh, that's brilliant. Let's add that to our notes. How can we tell something is an exponential function? The variable is in the exponent. You know what else? We should probably make that a question on the left. How do you know if something is an exponential function? All right, I'm not going to write it out, but you could write it out and get it into your Cornell notes. All right, now I want you to consider the simplest form of an exponential function, and that's when this value of a right here is equal to 1. If that value of a is equal to 1, then what we really have for the function is y equals 1 times b to the x. But 1 times anything is itself, so what we really have is just y equals b to the x power. So we're going to start here and really look at some of these bases, how they change, and how that affects the graph. Okay? So let's investigate. Now, when we have this basic form of an exponential function, y equals b to the x power, obviously b represents the base, and x is in the place of the exponent. Let's focus on b. When b is a value between 0 and 1, something specific is going to happen. In this case, we're going to have exponential decay. What that means graphically is that something will decrease, but it will not decrease in a linear fashion. It won't decrease in a straight line like this. That's not going to happen. And it won't decrease like a parabola, kind of like that. When we see things that exhibit exponential decay, they decay very quickly at first, and then they start to level off. So that's a graph of something that is exhibiting exponential decay. Now, what we're talking about here in terms of b, we're talking about values of b that are between 0 and 1. So for example, if b was equal to 1/2, basically what we're saying is every time period, whatever value you have is getting cut in half, and then getting cut in half again, and then getting cut in half again. Other values of b that could work in here besides a half might be something like 2/3. You could have 0.8. So it could be in either fractional or decimal form. Okay? Now the other possibility is when b is when b is greater than 1. Anytime b is greater than 1, we're going to see a graph that exhibits exponential growth. So what this looks like in the graph is basically the opposite of this. It's almost as if this had been reflected in the y-axis. So we're going to see something growing very, very slowly at first, and then all of a sudden it starts to take off and get really big really fast. That picture is a little bit exaggerated, but it exhibits those qualities, right? So we kind of see a gradual increase, and then it starts to get bigger faster. So you can see the curve is much different than a parabola, and obviously a linear function doesn't even have a curve. All right, so when we are exhibiting exponential growth, we could have values of b like 2. If b was equal to 2, that would tell me that whatever we were looking at was doubling every time period, or for each equal x interval, my value was doubling. But you could also have b values that were fractions, so like if b was equal to 3 halves, that's still a b value that's bigger than 1. 3 halves is really like 1.5. So it's still going to be exhibiting exponential growth. And of course, we could also have b's that were, decimals. It's probably more likely than anything else that we would exhibit a growth factor that was a decimal. All right, so now let's look at how to actually take that value and construct a graph out of it. Now remember, b is what we're calling the base. The base is the value that's being raised to the power, or the exponent. All right, so I'm going to show you how to graph these two different ways. First, we're going to look at how to graph a function using a table of values. A table of values is always a go-to method. Plug in values of x and get out values of y. It works every single time. But then we're going to look at a little shortcut way. Look at the base here, and that's going to tell me about the growth or decay factor, and we'll be able to make our graphs a little bit more quickly. When I'm constructing a table of values, you absolutely, especially when it's in this most simplest form, you absolutely positively must include values around a y-axis or around the origin. So I'm going to include values of x that go just like you do with a parabola, -2, -1, 0, 1, and 2. So I'm going to look at those 5 values to begin with. But when we're working with exponents, I'm actually going to start with the 0 first because it's easier, and we'll deal with the negatives last. So if x was equal to 0, y would be equal to 3 to the 0 power, but 3 to the 0 power, like anything to the 0 power, is 1. So we'll put that here. If x was equal to 1, we'd have y is equal to 3 to the first power, and of course 3 to the first power is 3, so y would be equal to 3. If x was equal to 2, now we'd have y equals 3 to the second power. That means 3 squared, or 3 times itself, 3 times 3, and that is 9. But what if we had x was equal to -1? All right, now this isn't like any more difficult. We just have to remember how to deal with negative exponents. That's going to be 1 over 3 to the first power, or 1/3. And if x was equal to -2, then y would equal 3 to the -2 power, or 1 over 3 squared, and 3 squared is 1/9. That's a pretty small value, right? So let's plot these points and see how well I can graph them. So if x is -2, y is 1/9. That is a pretty small value. In fact, it's pretty close to the x-axis. If x is -1, y is 1/3. So it's a little bit bigger. 1/3 of the way between 0 and 1 in the y value. And if x is 0, y is 1. And I want you to pay attention to this point because that particular point is going to become very important when we talk about how to graph these functions without using a table of values. 0, 1. Remember, anything to the 0 power is 1, right? All right, so my next point is 1, 3. If x is 1, y is 3, like this. And my next point, my last point, is 2, 9. Now, obviously, my graph isn't big enough for this, but we'll just kind of approximate. 2, 9 is probably going to be somewhere like way up there. Now, you can kind of see what's happening in this pattern. We know that with an exponential growth function, we're going to have very slow growth at the beginning, And then all of a sudden it's going to start getting much bigger, much faster. And so this is kind of what that function will look like. Of course, it would be a little bit smoother than the curve that I drew, but I didn't do too bad. All right, so we can always use the table of values to construct an exponential function. All right, but let's look and see if we can identify a quicker way to do it. So if I want to graph a exponential function without doing a table of values, the first thing that I want you to remember is the initial point. Now, obviously, this guy is still in the form of y equals b to the x, right? It's still a very simple exponential function. It's not a times b to the x. There's no, like, we're not adding. It's not 2 times a half to the x plus 6. There's no transformations involved here. We're not shifting it up or down or left or right. But we're just trying to get a good sense of what that base, for example, in this case it's 1/2, that base is doing to the function. So the initial value of any function in this form is going to be 0, 1. The reason it's going to be 0, 1 is because when x equals 0, anything to the 0 power is equal to 1, right? So if I plug in x equals 0 here, 1/2 to the 0 equals 1. Now in this case, the base is telling me my growth or decay factor. Since my base here is 1/2, and that's between 0 and 1, it's decaying by 1/2 for each unit of x that we increase. So what we do is we look here and we say, all right, my initial value is 1/2, and I'm cutting that in half as I move forward. So half of 1 is 1/2. Half of 1/2 is 1/4. Half of 1/4 is 1/8. And we just keep cutting that y value in half and in half and in half as we go out. Now this is the hard part. This is where we have to think about going backwards. If I'm multiplying by 1/2 going this way, then going this way I'm doing the opposite. I'm dividing by 1/2. But here's the cool thing. Dividing by 1/2 is actually the same as multiplying by 2. Let me show you an example. So here my y value is 1. 1 times 2 is 2. And then if we go back one more unit, 2 times 2 is 4, right? And this makes sense because it doesn't matter where I start. As I travel this way, as I travel to the right, my y values are getting cut in half. So for example, if I started right here, where my y value is 4, cut that in half, and we get a y value of 2. Cut that in half, and we get a y value of 1. Half of 1 is a half of a half is a fourth, etc., etc. So, as we travel in this direction on the y, or excuse me, on the x-axis, my y values are cut in half. In other words, they are divided by 2. But if I'm going in the opposite direction, if I'm going to the left, then what's happening to my y values are they're getting multiplied by 2. Okay, they're getting divided by 1/2, which is the same as multiplying by 2. And so if we put all these smooth, yeah, I can't really do this very good on this tablet here, but you get the picture. Connect it with a nice smooth curve. You can see it really gets really big really fast to the left, but it levels off going to the right. So the key picture, or the key thing in graphing a function where you have it in the form of y equals b to the x, identify the growth or decay rate, identify the initial value, which will always be 0, 1, and say, okay, I'm going to multiply going this way and divide going to the left. Let's revisit the previous function that we did, y equals 3 to the x. What this means is I'm going to start at my initial value of 0, 1. As I go to the right, I'm going to multiply by this base. by 3. So I'm getting bigger because it's growth. As I go to the left, I'm going to divide by 3, or, that's the same, by the way, as multiplying by 1/3. So as I go to the right, the y value, 1 times 3 is 3. My value, 3 times 3 is 9. As I go to the left, 1 divided by 3 is 1/3. 1/3 divided by 3 is 1/9. 1/9 divided by 3 is 1/27. Really small, very close to the x-axis. So I'm going to have you guys practice graphing some functions in this very basic form of y equals b to the x, focusing on different bases, and try to construct those graphs without doing a table of values. Then, if you need to do a table of values, always use these x values of -2 to +2. In the next video, we're going to look at how to transform those functions left, right, up, down, but mostly we're going to focus on the stretch factor of those functions. So changing them from b to the x to a times b to the x. What does that a value do? How does that change my function? And then, what if I flip it upside down, left, right, up, down, all of those things?